do is, what do we do when we don't know where to start? For example, if I have this third-degree polynomial, x cubed plus 2x squared minus 11x minus 12. What we have done in the past is that we would try to factor it. One of the tricks that we did for factoring was the fact that we would say, hey, if there are 4 parts to the polynomial, always try to see if you can group it via GCFs first. So when you sit there and start looking at it, you would say, okay, between an x cubed and a 2x squared, if I try to look at it in terms of GCFs, I would try and group, and I would take out an x squared and give me an x plus 2. When I get to the next one, there's nothing that I can factor out that will turn into an x plus 2, is there? No. So that means that I can't factor it in a sense that we have in the past. And not knowing what to look for, because I'm not saying, hey, f of 3 is a 0. I'm not giving you that information. You have to be able to decide, how do you figure out where your zeros might possibly, be located. And the way you do that is the following. You take the factors of your constant divided by the factors of the lead coefficient. That leading coefficient will always be the highest degree. So don't get tricked if it happens to go out of sequence. It happens to say x squared plus 3x cubed. You know what I mean? It might trick you like that. So it's all, bless you. So what we do here is this. What are your factors of 12? Okay. Now in this case, they're talking about negative 12. So you'd have plus or minus 1 times or plus 1, negative 12, or negative 1, positive 12. So with all of these, there's going to be some sort of variation with your signs. So it's always going to be written as plus or minus 1, 2, 3, 4, 6, and a 12, divided by, well, what's your lead coefficient? I don't rewrite plus or minus 1 in the denominator because it's busy work at that point. Because if I have a plus 1 divided by a plus 1 isn't going to be, it's going to be positive. If I have a negative divided by a positive, it's, you wind up canceling out and double counting things. So it's not worth it. So the reason why we do this is because a third degree polynomial with a 12 as a constant and a 1 as the leading term coefficient could possibly have 12 different zeros to check. Okay? So the reason why we try to write these out and list them out is because I know that on ACT tests, I've seen a question where it's written, how many possible zeros of a polynomial are there? Well, you'd have to know how to do this to be able to figure that out. Whereas if you had to just, instead of just being a third degree polynomial, you would say, oh, it's 3. When in essence, there are technically 12 possible in this case. Okay? Of that 12, only 3 of them will work. Okay? So this is what we're doing. We're taking the factors of the constant, and we divide it by the factors of the leading term coefficient. And we just count. This gives us 12 possible zeros. Okay? We're not finding them, we're not worrying about that, but we're just going to do that for right now. Not terrible. The worst thing that's going to happen is you're going to have to remember how to figure out find zeros. For example, let's move this all down. List the possible zeros for the following. Yes, sir. Yes, sir. List the possible zeros for the following. X cubed plus 14x squared plus 41x and then minus 56. I'll show you in a minute what happens when you don't believe this out. It's pretty easy. It's just an exercise. So here, the first one, you have to look at all the factors of 56 divided by all your factors of 1. No? Hmm. Do you remember your rules for finding if something is divisible by 3? You add them together, and if that's divisible by 3, it works. So what's 5 plus 6? 11. Is that divisible by 3? No. Let's go to the next one. 4. Easiest thing to do is just start thinking in terms of shortcut math. 4 goes into 5 how many times? How many are left over? 1. 4 goes into 16 how many times? 4. So 4 works. Okay. D. Does 5 work? No. Remember the trick? Remember the trick for 6s? Yeah, exactly. 6s work if only 2 and 3 work. Okay? If 2 and 3 work, then 6 will work. The 3 didn't work, so that means 6 isn't going to work. The 7 work. Yes, sir. You'll have a calculator. You may not have your fancy calculator. Thank you. And then you have what? 7, 8, 16. Was it 16? And then not 16. I'm sorry, 14. Sorry, I was thinking it was 4 goes into 16. Sorry, so it's 14, and then 28 and 56, all divided by 1. So this one has, let's see, 2, 4, 6, 8, 10, 12, 14, 16 possible zeros that you could come up with for a third degree polynomial. Yeah, they're all plus or minus. That's why I was counting them as two comparison twos. Because it's positive 1, negative 1, positive 2, negative 2, and so on. So I tried 72. 2, 4, 6, 8, 12, 14, 16.
So are you just getting the 1 then as like for the denominator?
Because your leading term coefficient is 1.
Yeah.
After this one, I'll show you what happens when you don't have that. I will say one thing, if you constantly go back to using your calculator each and every time, you'll run out of time. Now, if I look at the next one with the 72, I have the factors of 72. Let's see, 1, 2, 3, 4, 6, 8, 9, 12. It's really quick to get a ton of these. Okay, it's really, really quick to get a ton of these. Especially when you start looking at, 72 or 144 and so on. You just, it gets out there real fast, all right? That tells you have 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22, 24 possible zeros of this third degree polynomial. Why is it plus or minus? Because 1 times 1, or 1 positive 1 times positive 72 is positive 72. Negative 1 times negative 72 is positive 72. So you get those combinations of the plus minuses. Is that what you're going to say, Nelson? Yeah, that's why we have plus minuses here, guys. Because you can have negative 1, negative 72 gives you positive, and so on and so on. Yes, yeah. Some people do it that way. I've always been one that just goes up. Yeah, you can go that way. There's no rule. There's no rhyme or reason for which way you go. Either one is fine. Okay. Now the weird stuff happens then when you wind up with values that are not as clean. So I can clean the screen here. So when we have something like this, when you have a first term that has a coefficient that is not equal to 1. So if I have 2x cubed plus 7x squared minus 7x plus 30. What happens now when you list out all your possible zeros is that you might get duplicates. And that's where it takes a second or two extra to go through this one. So you do the same thing like we have it. We list out all of our factors of basically our tails. My 1 is at 30, the other one is at 2. So I'm listing all my factors of 30 divided by the factors of 2. Well, that's going to give me plus or minus 1, 2, 3, excuse me, 5, 6, 10, 15, and 30, all divided by 1 and 2. And that's where we get now. Now, in this case here, what happens is you get two sets of possible solutions. You have 1 divided by 1, 2 divided by 1, 3 divided by 1, and so on. So you wind up with plus or minus 1, 2, 3, 5, 6, 10, 15, 30. But you also get 1 half, 2 halves, 3 halves, 5 halves, 6 halves, 10 halves, 15 halves, and 30 halves. Well, that's what I'm getting at. Most people right off the bat go, do I have to write them out if they're duplicate? No. If you recognize right away that 30 divided by 2 is 15, which you've already counted, don't write it down. I usually write them down, especially the first few times that I do this, just because of the fact that I want to see what's going on. So as I'm going through my list, I've got 1, 2, 3, 5, 6, 10, 15, 30. 1 half. What's 2 divided by 2? 1, which you've already counted, so I don't worry about it. 3 halves. I don't have. 5 halves. I don't have. 6 over 2 is 3, which I have, so I don't count it. 10 over 2 is 5, which we have, so I don't count it. And the same with the third. If you, yes ma'am. Either way, and that's usually, I like to write them out and then go back and double check and cross them off because it forces me not to miss one. But if you want to go ahead and know that as you're writing them out, as you're seeing it, 2 over 2, oh, that's 1, I don't have to write it down. 3 over 2, I don't have that. 5 over 2, I don't have that. 6 over 2 is 3, I already have it, don't write it down. If you do it that way, that's fine. There's nothing wrong with that. I'm just old school and I take up more space than I need to. Yes, ma'am? Yes. You then have to, and if you do write out your duplicates, you have to go back and cancel them out. And that's just what it's making you do. It's making you go back to double check. So in this case here, as you go through it, when you have a leading term coefficient, it's really easy to have multiple possible zeros, like right away. I mean, here we go. 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22, 24. So you have a possible of 24 zeros that you have to theoretically check to see which ones are factorable. Okay? And the reason why I'm saying check the zeros if they're factorable is because what happens if you get a 0? What happens to the degree of the polynomial when you factor one of the zeros out? It goes down a degree, which then you drop, if this one was a cubic one, I believe, right? That means it drops it to a squared polynomial, which means you can probably factor that by hand. So even though you see that there's going to be 24 possible zeros that you have to work with, you might get a 0 after trying 2, and it just becomes quicker. Because as you've noticed, I know all of you guys practiced synthetic division big time over the past 5 days. I did nothing but teach my children synthetic division. That's what they need to learn. So we just go from there. All right. Try the other one real quick. See how you do on this one. List out all my possible zeros. What's that? It's not bad. It's actually, if you're right, you'll find out it's really short on this one. Does any of this, does it matter that you're missing one of your x degrees? Right, it doesn't matter. Oh, that's what it means. And that's all you have to worry about? So if you did it the other way, like you were saying, do I have to write them all out? You would have just written that and it would have been fine. Because in this case, it's pretty quick. Because you know that 5 over 5 is 1, 10 over 5 is 2, which you have already accounted for. In these cases, when you don't have that many factors, I wouldn't really worry about writing them all out. But when you have a ton of factors, it's easy to miss one. That's usually when I write them out for. Just to be more specific and to be on the safe side, shall we say. Okay. Excuse me. Questions on that? Okay, let's go to the next little bit of this. The next little bit of this talks about using synthetic division to determine whether or not something is a zero. So what I want to do is I want to use the numbers of 1, -1, 2, and -2 to determine if any or all of them, or some of them, are a zero of the function of the polynomial 2x to the fourth minus 9x cubed plus 8x squared plus 9x minus 10. Again, this is another practice run of what does it mean to be a zero of a polynomial. If it means that you are a zero of a polynomial, therefore that you know you are a term that could have been factored out. So what was the process for synthetic? I know I know you guys are lying to me. You did not do any synthetic division over break. I get it. I didn't either. It's okay. What was the process for doing that? Take a zero, draw the line, coefficients. Fourth degree polynomial means how many parts should be in our polynomial? 5. Do we have all 5? Are they in descending order? All right, guys. 2, 9, 8, 9, and 10. What was the first rule for synthetic division? Drop the 2. Now, when you drop the 2, what do you do to the 2? You multiply on the outside, so I'm going to multiply it by 1. And now what do you do on the inside? You add. Good. So 7, multiply, add, multiply, add, multiply, add. Hey! 1 is a 0. So if 1 is a 0, what's its term? Good. So 1 is a 0, so it's x minus 1. Now, that's one of them. How many more do we have to check? 3. Very good. Change that to -1. Grab an eraser. Or just rewrite it. Yeah. These next couple of sections, guys, is where you will wind up using a little bit more space or going through an eraser, just because you're doing the same thing over and over again. And as you start practicing through this, it works itself out pretty quick. And hopefully by now you're starting to get good at synthetic division, where you might recognize problem, you may not need to do the whole thing before you realize that you're not going to get a 0 at the end. And that happens. So let's see, multiply it out. Oh, did I screw something up? No. Yes, I did. I subtracted. That's 19. Hey, negative 1 is a 0, which means its term is x plus 1. And guess what we do now? Again! Add a 2. What's that? Yeah, you can do it that way too. But what happens is, if you don't get a 0, you can just restart at that point. You don't have to restart at the very beginning. Because if you think of it this way, if you know that 12 is written as 1 times 2 times 3 times 2 is sorry, is 12. That means is if you got to the 3, you still have 2's and 2's to go. If you got to the 2, you still have a 3 and a 2 to get to. So it doesn't matter the order in which you find them. But if you do get to one where it's not a 0, just restart at that point. Okay. So if I go back and just restart, it also works here. So 2 2 is 4, negative 5, negative 10, negative 2, negative 4, 5, 10, and a 0. Hey, 2 is a 0. So it's in x minus 2. Now I check with negative 2. And you can probably tell right about now, oh, well, it's not going to work. And as you get into this, you'll start to pick up on, wow, that number's not working right. Yeah, so I'm going to say no. So I know that as I get going, what you did is you got your zeros right off the bat. What were you left with when you factored out those 3 zeros? What was left as your constant term? Oh, you erased it. Oh, okay. So we know that 1, negative 1, and 2 were zeros of that function. There's still another 0 out there. What was left in there? So x minus 5, so that means that 5 over 2 was the last 0. Because then you're left with that column. And that's what this is going to allow us to be able to do as we go forward on this. Because remember, every time you take a 0 out, you're taking out a term. And within that term, it drops the next polynomial's degree because there's one less thing to multiply out. It's totally up to you because if you keep dropping it down, let's see, we'll try the drop down one in the next one. Okay, we'll try that other method on this one here. So we'll do the same thing with plus and minus ones and stuff. So 1, negative 1, 2, negative 2. We'll try the other method here. I'll show you. 1, 5, 2, negative 8. We'll try it right off the bat with 1. The other method, what we were talking about is, let's say 1 winds up being a 0, and then I just use that smaller polynomial as my next setup to factor with. Okay? Instead of starting over with the third degree one, I'll start with the square. So I try it with 1. First step, bring down the 1, multiply, add, multiply, add, multiply, add. So 1 is a 0, which makes its term x minus 1. Okay? Now, use this one as our next bit. I'll try it again at negative 1 here. I only have to go through 3 parts because the 0 wound up here and I don't have to worry about it. I try negative 1, I get 1, negative 1, 5, negative 5. That did not work. So I erase it. And at that same point, then I'm going to try my next number, which was 2. I don't have to go back to 1 excuse me. But I go back and I'll go into 2. I go to 2, I get 1, 2, 8, 8, and that didn't work. 16. Well, that still didn't work. I tried that at negative 2. And it worked. So then I wound up with a 0 at negative 2, which leaves me x plus 2. It started at a cube, a squared, which means this is an x to the first degree, which means this is now x plus 4, which means your last 0 would be located at 4. This is what synthetic division allows us to be able to do. Now, had I started that problem to begin with at negative 2, instead of starting at 1, it wouldn't have mattered. It doesn't matter the order in which you multiply things together, because if it winds up being a factor, it's still going to come out in the long run. Okay? It still works itself through. You know, so if I did do this one starting with negative 2, if I start this one at negative 2 instead, it's still a 0, isn't it? It's still a 0. And I can go and try it now at 2. If I try it at 2, it won't work. But if I go to negative 1, excuse me, that didn't work. It should have worked. Oh, okay, thank you. And you can still get possible zeros. Okay? It still works, and what are you left with here? And you still had a 0 at negative 2, 1. The order in which you find zeros doesn't matter. Sir, remember how every time it goes down a degree? Every time you find a 0 when you synthetically divide, it drops it a degree because you took out a term. You took out x plus or x minus. So if I started a cube, the next one becomes squared, and after squared is x. Because these are your coefficients of your polynomial. So technically this one here is x squared plus 3x minus 4, which you should have been able to factor that right away. What times what's negative 4 you add together to get 3? 4 and negative 1. X plus 4, x minus 1. A lot of times as you get that first polynomial part factored, it gets you to a point that you'll be able to actually factor it in the sense that you like an x squared term. Yes, ma'am. What do you mean? No, you can go start from the beginning every time. I will suggest to try it this way a couple times. Reason being is because every time you start that, it drops it a degree. Okay? Like we were just saying, this one was your x cubed, x squared, x, and your constant. Those were your coefficients, which made this one here x squared plus 3x minus 4. What times what's negative 4 you add together to get 3? You get x plus 4, x minus 1, which happen to be here and here. As you constantly drop the degrees, remember that you are coming up with new coefficients of a lesser degree polynomial. Yes, ma'am? What do you mean? And that's the idea. I would start doing it more and more this way because as we get into it, eventually I'm just going to say, hey, knucklehead. I'm just going to say final zeros. find all the zeros of that, which means you would have to find a place to start with. Means you'd have to figure out all the factors, in this case of 18, divided by all the factors of 1, and synthetically divide all the way around. And as you find a 0, remember that it drops a degree, then you just constantly keep going and going and going. Okay? There will be a couple of little tricks as we get into this a little bit further that I'm going to explain to you guys. I won't worry about that until Wednesday, because there is this little tricky thing of multiplicity. What did multiplicity mean again? Yeah, it changes direction at a duplicated 0. Remember when you have a duplicated 0, it changes direction on that axis? It is easy to find multiplicity with synthetic division just by checking that same 0 twice. So if it works once, if you try it again, then you know it has, and it works, and then you know you have multiplicity. If it doesn't work, you're no loss for anything because it only takes a minute to synthetically divide. Yes? It will, because as you go through it, we're going to get more and more complicated polynomials that you'll have multiplicities thrown in. Okay, so we'll get there. I think I already posted what I had you guys do for this evening, if I'm not mistaken. I didn't put the numbers on there? Oh, I'm not sure. Yeah, I know. Oops, wrong one. If I'm not mistaken, well, it so happens to have a book right here. I can tell you what numbers they are. I want you guys to do numbers. Why aren't you? Scroll. I want you guys to go from 16 through 36 evens on this. Yeah. I just leave it up here real quick if you want to take a look at it. The first 4 of them are list out all the possible zeros, and then the next 5 are check if 1, -1, 2, and -2 work. And then I gave you 2 at the very end that I want you to factor and find all the zeros. They are asking just for real zeros, so if you just find the real zeros, that's fine. Otherwise, if you want to be rambunctious, find all zeros because it works with imaginary too. Just think about it. Good. Yeah, we need those. What's up? 16 through 36 evens. Yeah, I'll put it up here in a second. Yeah. List all possible zeros. I just figured that way it would fit on here if I just left it up.